with DES and any type of cryptography is, there needs to be a way for us to protect sensitive information. And it starts with symmetric cryptography, which we were just talking a little bit about. But the history is long and it's rich. And it starts really with the National Institute of Standards and Technology, or NIST. So the need for the protection of any sensitive information started to come up back in, I guess, the early 60s, and moved into the cryptography program in the NIST in the early 70s. And so NIST went through and started to invite smart people to submit ideas for ways, that could be encrypted. And the idea was that the National Security Agency, or in the NSA, would be able to take this algorithm and apply it to any type of comms or communications that they wanted to. And they named it the data encryption. I had a piece of the pie back in the 70s to help, because they were really good with financial transactions. And they actually had an algorithm that was kind of interesting name called Lucifer. And that algorithm was accepted, but the DES program started to come in and figure out what's going to be the strongest and most efficient way to have encryption implemented within any environment across the world. And so, that really was one of the big deals of modern encryption, was the symmetric encryption, DES, or the data encryption standard. And it really got into doing a lot of different things. But we're going to talk about DES here in a little bit more detail. So with DES in your book, you can follow along in your book to just kind of take a look at it here. There's going to be 5 different modes. And, it's kind of fascinating to me, at least, that with DES, it started in 1974 and it lasted until 1998. And it's quite interesting that, with DES, that the 24 years that it lasted, it has the 5 different modes, is what we typically will call them. 5 different modes. And those modes are quite important in that we need to make sure that you understand these, because you may end up seeing them on the exam. So let's start off here with the ECB and see if we can try to identify, at least at a high level, what it does and why it's important for you to, at least at a very high level, understand what's going on with it. Give me a second. All right, so one thing to note here is that DES is a block cipher, which means that the data is broken up into segments, and each segment is encrypted. Okay. Now, if you thought about it, any block cipher that's out there, they would have a certain way where you take the plain text. We went through this yesterday. So you take the plain text here, and you then may segment it up into these symmetric blocks here. So each one of these blocks may end up being part of the plain text. And then each one of these would then get encrypted. So this is the encryption algorithm. And then it becomes ciphertext right here, just at a very high level, right? And so there's different methods that DES uses. One of them, to start off, is the electronic code book. And then there's cipher block chaining, which this has become, this concept of block ciphers or block chaining has become even more prevalent now than ever with modern day Bitcoin and cryptocurrency. A lot of times you'll hear people talk about blockchain, and that's really the derivative from DES is a blockchain. Now it's a little bit more robust right now than ever, but that's really, that cryptocurrency comes from this as at least initially. Cipher feedback mode or CFB, output feedback, and then a counter. So let's go through and just talk about these at a really high level. The first and foremost here, first and foremost that we're going to have is, you can follow along with me in your book if you want. First and foremost one that we're going to have is this one that's called electronic code book mode, which is the ECB here, and then we'll jump into these other ones here after that. So ECB is they call it a code book, and really what it does is it breaks it up into these 64-bit blocks. And these blocks take the plain text that I mentioned here, and then it chunks it into these blocks for quicker processing. But it also incorporates this thing that's called a pad. A pad. And in the terms of passwords and password protection, you may have heard of a salt before, where it adds something in there for parity. And so really this 64-bit block here in this electronic code book that's created with DES becomes a 56-bit key and 8 bits pad for parity to try to throw off any would-be attackers. This is a pseudo-random generated number. Or these 8 bits are pseudo-random, where it'll actually go and create a pad for each block to allow some sort of parity. So if you're looking at the block here, it's 64 bits altogether. There's going to be 56 bits that it's going to the plain text will get encrypted into ciphertext. And then over here, this will be the pad. So the entire thing that altogether here is 64 bits. And so that starts the party here with the code book that really dictates how a block of text will be encrypted and decrypted. So from that is, and I say that it's a pseudo random because that was really one of the biggest problems with DES is that there's not enough randomness in this. It's more of an obfuscation. So and that's one of the reasons why it was cracked. So not enough randomness in that. But I mean, it lasted a really long time, right? So almost a quarter of a century. Uh, because this mode works with blocks and the data independently, then a data within a file does not have to be encrypted in a certain order. It can, it could do this one first, then that one, and then that one, because if you're using like in databases and you have pieces of different information that's accessed in different times, if you're using this electronic code book, then any record in any table in a database can be added or deleted, encrypted, decrypted independently without any other table records. And that's kind of a neat function with this ECB, this mode, if you will, with DES. And so at a high level, that's really how that works. Whoa. There we go. So let me go over here. So what this means is with at least with the ECB is that everything I just said is that the operations for everything, like how it works with ECB, electronic code book, operations can be run in parallel, which gets for quick processing and allows you to decrease any processing time. If there's errors, then the errors are contained within and not given for any potential attacker as an error message or anything like that. Typically, you would use an ECB for short messages, instead of a huge, 10 gig file or something like that. One setback is that it can't start processing the encryption scheme, processing the encryption for this one. You need the plain text. In order to process the encryption, you need the plain text. And so that was kind of a setback for ECB. Okay. And so the next one here is the Cipher blockchaining. Or CBC. And, at a high level, you may have one of these on your exam. These 5 modes, it's very likely that you won't have any of these on the exam. So I'm just letting you know that even though we're going to review these, you may not need to retain them, but definitely at a very high level, understanding would be helpful for you. So check it out here with CBC here, the ciphertext here. This is kind of neat. This is the first time that this was presented. The ciphertext from the previous block of data is used in encrypting the next block of data, which is kind of cool. So why? Why is that interesting? Well, this particular one means that, if you have uh, uh, a word, let's say that we have a word, and then the example that they give in the book is the word balloon is the word. Okay, and that the plain text of balloon here gets put into the cipher block chaining, and the resulting ciphertext may be, HWIC, something like that, something random. Each time that it was encrypted using the same key, the same ciphertext would always be given. So, if you have the key and you're using the encryption algorithm right here, then the same ciphertext would always be given. So if that was the case, then attackers could predict a pattern, and that's what attackers are looking for. Attackers try to find patterns and then predict, right? And if they can do that, then your encryption scheme is broken. So this was a problem with symmetric encryption, is that if you have a key in the algorithm, well, with the algorithm, there's a principle that a guy named August Kirchhoff created, who said that if your algorithm's good, share the algorithm with the rest of the world. Share the algorithm with the world. And Kirchhoff postulated that, hey, you know what? If we have all these smart people all across the world, and you're saying that your stuff don't stink, go ahead and share it, but don't give us the key. Let's see if we can break it, but don't give us the key. And so that Kirchhoff's principle came into play, and with DES, they decided to do something a little bit differently, because what it does is this CBC, especially, this mode does not reveal any pattern because each block of text, the key and the value on the previous test are processed and applied to the next one, which is kind of cool if you look at it right here, right? So you have plain text here. You put the plain text into the encryption. The output of that becomes ciphertext. You take that ciphertext, and really that ciphertext down here, quote unquote ciphertext, gets put in as the plain text. You encrypt it, and then now that becomes really ciphertext 1 plus ciphertext 2. And then again, you do it over here, run it through the encryption scheme. But really, it's a little piece of the previous by going through this methodology. And by doing that, this gives you dependence between the different blocks here. So if ciphertext 1 is added to the next block, and now we have, so remember, this is a block cipher. So if we have all these blocks of data that we're chunking up, and we take this plain text, and then we run it through this scheme. This plain text now becomes ciphertext. Well, then we take that ciphertext and we add it to the next plain text. So now that becomes the plain text and ciphertext from the first one, and then that's encrypted. And then now it's plain text 1, that's ciphertext, added to plain text 2, that's ciphertext, and then now that becomes even more cipher, and it keeps going and going and going and going, and because we're all chaining them together, uh, it's able to hide any patterns. And this was a breakthrough whenever this came out. Uh, so something to think about if you've never seen anything dealing with Cipher blockchaining. Now you can kind of think about it in this way, that this is why some of the Cipher blockchaining and the cryptocurrency currently is very popular. Another way to look at it could be this right here. Look at that right there. Boom. Oh my God. Yeah, maybe that's not how you want to look at it, but if you have, plain text here, and that plain text is put into some sort of encryption, come on, there we go. Then now you have some ciphertext. So hopefully that made you kind of roll your eyes or smile or something this morning. So that's Cipher blockchain. The next type of mode here with DES is the hold on, before we go to the next one, any questions on that CBC? All right, the next one here is the Cipher feedback mode, or the CFB. And the CFB is really it gives us a combination with the block cipher and what's called a stream cipher. So instead of it just doing all these 64-bit blocks, it also will individually encrypt each particular character as it comes through with what we typically will see is this, what's called an XOR. XOR. And if you're not familiar with XOR, you may want to become a little bit more familiar with it. It provides this thing that's called an initialization vector. Initialization vector. That is just a pseudo-random character. Pretty much if you think of it like a password that kind of gets it going here. The password or initialization vector, it kind of starts it off. You provide the key to that algorithm, the DES algorithm, and then now it gets into this big pool of what is typically called a key stream. So we take the plain text and we pass it to this key stream and it becomes ciphertext. So typically what we'll see is that this key stream is run through the XOR operand, and the key and the initialization vector are used by the algorithm to create a key stream, which is just a random set of bits. So if you're not as familiar with how the XOR process works, typically, if you go and do a little bit of research on it, typically people call it a truth table. You may see the XOR on the exam. So let's just go through and talk about that real quick, because you may see something like this on the exam. So let me just, this is the first time that we're introducing this. So many times you hear people talk about a XOR or a truth table. And because of that, this concept here could become something of interest to you. So let's check it out here. So with this truth table, we have different bits. Let's say that the bit is P and Q, and then together we'll say P and Q. Okay. So if we just kind of make a little matrix here, or table 1, 2, 3, 4, like that. And then over here, I'm going to do 0, 0, 1, 1, and then 0, 1, 0, 1. So if it's the same, if 0 and 0, if those two values are the same, it's always going to be 0. Like when you run it through this XOR operand, this operation, right? If it's different, 0 and 1, it's always going to be 1. So 1 and 0 would be 1. 1 and 1 would be 0, because it's the same, right? So for purposes of your exam, you may see something like this right here. You have a message, and the message looks something like this: 0, 1, 0, 1, 0, 1, 0, 1. You have a key stream that is, let's just say 1, 1, 0, 1, 1, 1, 0, 1. And now you want to have the ciphertext down below here. Well, if it's running an XOR operand here, we would go through and use our truth table. And the truth table, it's important here, this does not change. Never. Does not change. This is the truth table for XOR right here. So if it's the same, it's 0. If it's different, it's 1. So here, different, 1, same, 0, same, 0, same, 0, different, 1, same, 0, same, 0, same, 0. So the XOR in the ciphertext of this message with this key is that down there. I would probably bet a paycheck that you will have one question on XOR. Maybe not about Cipher feedback mode, but definitely the concept that was introduced with the Cipher feedback mode. There's a bunch of different programming languages out there that use this: C, C++, C Sharp, Java, Perl, PHP, Python. A lot of times you hear people say this is an XOR, or they say maybe a bitwise operator. And that was introduced with DES and the Cipher feedback mode. Something of interest for you, maybe. Okay, so that's Cipher feedback mode. So something that's similar, but a little bit different here, is the output feedback mode, this output feedback mode. So let's go through and define this really quickly. Again, this is all DES, output feedback. And I think it's OFB. So before I get into it, any questions about that last one? Okay, good. All right, so this one, output feedback, really the name kind of makes sense here. The output of each one of them is provided as feedback to the next one. So, um, this is a block cipher that is typically used if it needs to emulate a stream cipher, which is kind of confusing, but check it out here. If you have small amounts of data, we can have a smaller chance here of creating errors throughout the full encryption process. So with this output feedback mode, a lot of times the size of the ciphertext or the stream values, the key stream values, need to be the same size as the block of the plain text that's encrypted. Why is that? Well, if you have, let's say, a 64-bit block, then the key stream has to be 64 bits as well. Because if you're going to run a bitwise operator on it, right? We just talked about that, the XOR, then it needs to be these two values. You need to have a one-to-one way that you can make that happen. So if you're using the if you're using that methodology, or if you have this rule, then the ciphertext here and the key stream allows you to continually be able to encrypt using the same size as the block cipher, because we don't want to have it create errors. And so the output feedback immediately is kind of like a check to see if the plain text that was given is 64, we have a key stream of 64, then the output should be 64 here, because you're taking this and running the operation on it to give a piece of ciphertext here that is the same block size. And so from that, then that key stream would continue to be used. It's the output of it at the key in the next algorithm to encrypt the key stream for the next piece of plain text. And so it's almost very similar to that cipher feedback mode, where it'll give you some feedback and then it takes it to the next one, and then it'll give you some feedback and take it to the next one. Otherwise, we'd be repeating the values over and over again, and we don't want to have any patterns. So this is one of the modes, and then the last mode here is what's called the counter mode, or CTR, the counter mode. And instead of it going through and having that random, this randomly generated key stream here, what this actually will do is it has these counters that are at the top here that help to set or generate the key stream values for each one of these. And the counter in this particular case is XORed as well. That's what that little symbol is right there, the XOR. So each one of these is XORed to give you that operation, and it could help with performance as well to speed it up. Uh, usually, what we see is for asynchronous transfer mode, not to be confused with the automated teller machine, asynchronous transfer mode, whenever you are at your your headquarters building and you're trying to send data to somewhere else, let's just say company A, uh, what asynchronous transfer mode does is it will take a look at what you're trying to send, and then it'll break it up into chunks of data to pulse across the wire. And that's why even with like a fiber connection, a lot of times you'll see when you download or upload stuff, be it'll go here, 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 and then complete, because it's breaking it up into these chunks to push it across the wire. And so with each one of these chunks, maybe in asynchronous transfer mode, it would have a counter to tell you how to reorder it when it goes back onto the other side. And one of the primary things that uses similar types of technology, like the counter here, is IP security or IPsec. So that's really what the counter does here. It will be able to process the packets without having to wait for the full message to arrive, because it gives you these order. And so when you send it from one place to another, the place over here starts to, maybe they receive 4 first, sequentially, right? Maybe then next it'll be 3, and then next it'll be 5, and then next it'll be 1, and then next it'll be 2. Well, when you receive 4, you can start putting together the information, knowing that, you still have 1, 2, 3 that are not there, but you do have 4, and you know that you're waiting for 5 still. And then when 3 comes in, now you have 3. When 5 comes in, you have 5. And so the sequential, the counter here helps with sequencing and allows for the processing to begin without having the full message, which is kind of nice, especially when you're dealing with large amounts of data. All right, so that's really the 5 different modes of DES. Are there any questions? Any questions? Anybody still there? Okay, good. Okay, good. All right, so let me just ask a couple questions here. See if anybody was paying attention. All right, so there's the first one. Oh, no, I didn't share it. There's question. All right, good. Yeah, 64 bits. Uh, let's see here. I got a question. Homework, it asks for examples. Find 2 real world examples of all 5. Um, you know, uh, so to answer the question here, I had a question. Uh, in the homework, it asked for examples. Could you provide a real world example of all 5? Yeah. So, well, I don't know. I don't use this all the time, especially down in the weeds. But for the counter mode, IPsec, um, that would be one. Asynchronous transfer mode. Even sequencing of packets kind of work like this right here as it's going across the wire. Um, this XOR operand here, this would be um, a one-time password or one-time pad, an OTP. That would be a one-time password or one-time pad, which that was created in 1917 by a guy named Gilbert Vernon. You can't just make this stuff up, right? And he called it he had the audacity to call it the perfect type of secrecy. And here we are 103 years later, and homeboy was right. We still use that, the one-time password. But essentially, that's what this is right here. This key stream is really the one-time password, because this is really, the key stream is kind of like a pool of keys. That's the best way to kind of metaphorically think of it. And this pool of keys, and at least in the one-time password paradigm, is only used one time. And then once you use it, you can't use it anymore. So that would be an example of that one. This would be cryptocurrency, would be an example, I would say, about that. And then the ECB. I think the ECB is really just how encryption typically will work. I don't have an example of that one. And really, I don't have an example of for this one either, other than that the key stream, this concept right here, the key stream, so that pool of keys, continues to get larger with each time that it's run, because it just changes each time that it's run, but no, I don't have a good example for this one. Sorry about that. All right, so let me ask you a few other questions here and see if you guys are tracking with me. Yes, you are correct. That's a great point. SSH can use any of those. SSH can use any of those. Absolutely. Good. All right, let's talk, and I don't want to fall behind here because I got a lot of stuff that I want to cover today. So I want to make sure that everybody's on the same page with Des. And, when Des was broken, um, they decided to come up with triple Des. And, from there, decided that it needed to be much more reliable. And so what they did is they decided to run triple Des through 48 rounds of computations to make it much more difficult. So triple Des here, I'm just going to write it on here, is 48 rounds of computation. So when Des was broken, they started scrambling the fighter jets thinking about, okay, what do we need to do? And that's exactly what they ended up doing, is they came up with triple Des to try to figure out what is going to be the right way for us to make sure that this doesn't get encrypted or cracked, because we don't want it to be cracked. All right, let me just ask you some questions here, and we'll see. So this algorithm Yeah. Yep. So it's better for use for lower processing power, wireless device, and cell phone. That's going to be ECC. Good. So if we're talking about PKI, we're talking about PKI now, like shifting gears, right? I'm talking about PKI. What is the trusted third party that generates and maintains user certificates? Good. Alicia, no. Brandon, yes. Ryan, yes. Jennifer, yes. That's right. Good. The certificate authority. So with the certificate authority, there needs to be a way for us to keep track of those revoked certificates. So what is that called? Anytime a certificate is revoked. Yeah, good. Jennifer? Yes, good. Alicia, no. Amos, no. Ryan, that's close. Yeah. So it's called the certificate revocation list. Sometimes people say the krill. You'll hear people say the krill. All right. So the certificate authority usually has these that it uses to associate a public key to a person's identity. It uses these things. What does it use? The certificate authority uses these things. And I'll give you a hint here. Here, the certificate authority uses these things, and these things are in X509 format. What do you mean, Amos? Doug, yes. Jennifer, no. Okay. Yeah, X509 format, certificate authority uses certificates, right? So it creates this thing called a keyed pair. Let me just bring it up here. And with any type of PKI environment, it's going to have this keyed pair, and that keyed pair, oops, that keyed pair here, let's write that on here, keyed pair, is issued and created by this certificate authority. Now, this is oftentimes very confusing for a lot of people, but I want to make sure that we're all on the same page here, right? So PKI is typically software, right? If you got a lot of money, because it takes a lot of money to do it, if you got a lot of money, you can buy software that will allow you to create a public key infrastructure within your organization. And it's quite interesting because once you buy the software, now you take all of your users and they go through what's called a quote enrollment process. And that enrollment process allows them to go through and fill out some information, but essentially after they enroll with the registration authority, usually the way that I explain that is the registration authority is usually like your badging office, the people that work at the badging office. They'll be using this software, an interface with the software. They'll take your I-9 documentation. So the RA will take your, your driver's license, your birth certificate. They'll scan that in. They'll get your fingerprint. They may get a photo of you. So fingerprint, photo, and with the intent that they're going to end up probably creating some sort of badge for you. And in the DoD, that would be a smart card, right, or a CAC, right? So this enrollment happens. You get invited to come to the badging office, and the badging office is called the registration authority, right? The way that I kind of look at it, typically, and I know it may be silly here, is no one can talk to the certificate authority except the registration authority. Okay? So nobody can talk to the certificate authority except the registration authority. It's kind of like this right here. If you've ever seen the movie The Wizard of Oz, they go in, they're meeting the wizard, or they're walking down this hallway, they get ready to meet the wizard. Silence! So the certificate authority is kind of like the Great Wizard of Oz right here. So if you think of the certificate authority, no one is powerful enough to talk to the Great Wizard of Oz, right? And again, it is a piece of software, right? So you install this software on a server, and the software usually runs a public key cryptographic service application on it. And that PKCS application generates that keyed pair. So that certificate, no one can talk to the CA except for licensed brokers or licensed proxy people, which may be a registration authority, right? And like I said here, it's kind of like the badging office. You would go into the actual badging office, and you wait for an hour, and then you go and meet with the registration official. You give them your information here, and they scan it. They enter some data into it, and what it's doing is it actually will send the request up to the certificate authority. The certificate authority trusts the registration authority, and that it is putting somebody through an enrollment process. And so the registration authority submits the paperwork up to the CA. The CA then says, okay, here is the keyed pair. I've created the keyed pair for that person. Here it is. And so the registration authority then has a way that they maintain that information. And now that person becomes part of the cool people in the web of trust. In order for you to do anything inside of the PKI environment, you have to belong to the web of trust. And so when these keys are generated, these certificates are generated, they are in what's called an X509 format, okay? That X509 format is a schema that any certificate must adhere to. And that looks like this right here. So if you take a look at a certificate, it's in the X509 format. It must have these values in it. That's why sometimes if you browse to a web page and it has a certificate that's invalid, it's because one of these is no longer valid. Typically, it's the validity period, like it's expired for some reason. So these certificates are in what's called an X509 format. And, the file extensions could be something like a SIR, or I think there's like a PRM or something like that. Let's get rid of that. I don't know what that is. But essentially, the software creates the certificates in the X509 format, and then from there, you can be part of that realm of trust after that. Similar to what we looked at last night in the homework, and one of the reasons why I typically will bring that up here. If you look at this, the certificate authority is up here. Whoops. Not right. Oh, it says it's not responding. Okay, that's odd. So in the PKI environment, you have a user. User goes to the proxy, who is the RA in this particular one. And from there, the RA puts in the request. Boy, all hell's breaking loose here. The RA puts in the request to the CA, and then you become part of the realm of trust. Hopefully that makes sense to you. But if not, let me know. I just put something into the chat window. Good. Yep. That's right. Brandon, no. What's the format of the certificate? That's right, Ryan. Good. Amos, good. Alicia, good. Jennifer, good. Doug, good. What's the format of it? That's going to be an X509. X509 is going to be the format of the certificate. All right, what about, I'm just going to put in some random, and I'm going to close up this because we need to move on here, this domain. So this algorithm is based on a one-way function that factors large numbers into prime numbers, and it also is the de facto standard for digital signatures. Yes, that's right, Ryan. Good, Doug. Good, Brandon. Good. Yep. RSA. Good. Yeah, the prime numbers is the giveaway there. All right, so this hashing algorithm produces a 160-bit hash. Which one is it? Amos, yes. Alicia, yes. Doug, I don't think by default, Doug, that one does. And there's another one that's going to be on the test that's more popular than that one. I think you can configure that one to do that, but not by default. Brandon, yes. Jennifer, yes. Yeah, that's right, Doug. That's right. All right, so I think that it's prudent, even though I'm probably about 15 minutes behind where I need to be right now. I think it's probably prudent. I don't want to just throw things to the wayside here. I just put something in, and I want to make sure that you guys answer that. Uh, but I want to talk about hashing. I have to talk about hashing. This is one of my favorite things to talk about. But you guys are asking great questions here. All right. What is an attack on hashing functions through brute force? Yes, Amos, good. Ryan, no. Doug, no. Oh, thank you. Well, not today, but yeah. All right. So that's right. Good. Good, Doug. All right. So with any idea that we have, any idea that we ever have in this world, if it's internal, we think it's a great idea. Once we start broadcasting that out to the rest of the world, people always come back and say, that sucks. It's kind of like the news. If you ever watch the news, whether it's, PBS, NPR, Fox, CNN, whatever, usually it's bad news, right? Well, if we have good ideas, people will try to throw darts at them. And, for hashing algorithms, they're no different. So, how do you remember the hashing algorithms? What's the way mnemonically that you may remember the hashing algorithms? What's that? Okay, good, good. That's right. Amos, you left off the R, but yeah, other than that, that looks good. So with any hash that's out there, it is potentially susceptible to have what's called a collision. And let me share my screen. This is a neat topic if you've never had anybody explain it to you before. Um, let me see if I can do the best that I possibly can here. Okay. So let's say that I have a word, and that word is hello. Okay. Let's say my word is hello. So my word here is all caps. Well, if I have something like this hashing calculator right here, what I can do is I can put in the word hello, all caps, and I can get any kind of hashing algorithm, at least on this one, that's available. For me, I'm just going to do SHA-1 or SHA, regular SHA. I'm going to say calculate it. Okay, so this produces 160-bit hash. That allows us to have this value right here. So if you put in hello, into an online calculator, like let's say this one right here. Okay, yeah, sounds good. If I enter it in, so that says 256, I don't want that, I want this one. Generate a SHA-1 hash. All right, so if I have the word hello right here, this one sucks. Anyway, you can go out and find your own hashing calculator somewhere out there. But if you type in the word hello and you're looking for a SHA hash, you better get this SHA hash, right? So see if you can find a SHA-1 hashing calculator out there. What I have is, it's called a hashing calc, and it works pretty well. But you don't have to use that if you don't want to. So all I'm doing is recording it here in Notepad, and then I have a separate calculator. Yep, that's right. So check it out. That's my first result here for SHA. Now, if I come in here and do all lowercase, hello, and I type that in to my hashing calculator, right? Then I should get what? Type it in, right? All lowercase. I should get a completely different value here. Completely different value. Check this out. Those are two completely different values, right? Well, what if, I do bumpy caps? So uppercase H, lowercase e, uppercase L, lowercase l, and then uppercase L. How about I do hello spelt like that? I mean, they're all three the same word, right? So, well, no, they're actually completely different from a computer's perspective. So all three of these are different, right? And it's not just a little bit different, it's significantly different, right? So if we think about it, these three hello really put us in a position to kind of explain a concept that you may or may not be familiar with. These are all specifically different, right? Like completely different. So there's a concept that comes with hashing that is called interesting. There's a concept with hashing that is called the Avalanche Effect. So if I draw Mount Fujiyama here, I'm an American Ninja Warrior, right? And let's say that up top here is my hashing algorithm. Okay, so that's the algorithm. I have HELLO over here as my text. Over here, I have HELLO, all lowercase, right? And then over here, maybe I have HELLO, the bumpy caps right here. Some people say camel case, whatever. Hungarian notation is the actual academic way to describe that. So if I put in this plain text hello into my hashing algorithm, let's just say SHA here, right? I'll put it into SHA. And it should go into the algorithm and then give me a output that is 160-bit. And the output is going to be unique to hello. So it's 160-bit output for all caps hello. If I put in, hello over here, HELLO, all lowercase, then it should give me something significantly different all the way across the other side of the mountain. So if this was an avalanche here, right, we don't know where it's going to go. We don't know which way down the mountain it's going to go, but we know that it shouldn't go to the same spot as the other, because if it did, it would be called a collision. And so this one over here would be 160-bit output, and that would be all lowercase, whatever that is. And I showed you earlier that if you're using SHA and I'm using SHA, that these are the values, right? They're significantly different all the way across the other side of the mountain. But if I said, let's say I put in another word here, right? Let's just say another word, cyber, right? And I ran cyber through this algorithm. If that word right here, cyber, went through the SHA algorithm and produced this same hash right here, let's just say, for conversation purposes here, let's say that I type in the word cyber right here, all lowercase, and it gives me that. So now I got hello and cyber with the same values. Well, that means that that hashing algorithm does not adhere to the avalanche effect. And, we have forced what's called a collision. And so a lot of times what we see is whenever you publish your algorithm, kind of like what Kirchhoff was saying before, remember I mentioned that, when you publish your algorithm to everybody, people start throwing darts at it, right? They're trying to throw darts at it to see how awesome you really are, with the intent that they're going to try to break it. They're going to try to force that collision. And if that happens, then people lose the trust, they lose the faith in your algorithm, right? So, that's happened a number of different times. One of them that it's happened to is MD5. MD5 has had a collision in it at least one time, but probably even more. So I say that because this effect here, this collision effect, if an algorithm does not adhere to the avalanche effect, then a collision is likely. And typically, that collision is manifested through what's called a type of attack, which is a birthday attack. So let's go through really quickly and do a quick exercise on that. So check it out. If we're trying to test an algorithm, okay, for a collision, we can test it using a technique that's called a birthday attack. And that birthday attack looks at the total possible values, and using probability theory, it will allow you to statistically come up with a number using probability theory. And typically, if it's a finite key space, so it has ending, right? So it's not infinite. It has boundaries. So since it has boundaries, that finite key space, usually within right around 23 entries, we can force a collision. Okay, so check it out. If I was to just look over here at everybody who's on the horn, let's see who's all on the horn here. Okay, so let's say here that we want to draw out a matrix. Ben, Alicia, Amos, Brandon. This is how it's presented to me. Doug, Jennifer, Ryan. Let's say here that we wanted to do a little exercise here. Okay. What I'd like for you to do is provide me with 4 dates in the chat window, but do it privately, please. And those dates must be in month, day format, right? Month, day format. And don't just do a denial of service attack on me. Give me 4 dates in one message, please. Okay? Give me 4 dates in one message so I don't have to keep going back in there. But they have to be month, day format. Okay? Month, day format. So think of 4 dates. I mean, usually people put their birthday, their significant other's birthday, kid's birthday, or whatever. I don't care. Just give me 4 dates in month, and day format. All right, so let's see. We got Alicia, Jennifer, Brandon, Ryan. All right, so no year. Don't give me a year. And the reason is, check this out. So like I said before, in a finite key space, so it has boundaries. The month, day has 365, I guess 366 sometimes, possible entries. So it's finite, right? It has a boundary. Whereas if I put on the year here, it would be exponentially more, because we could go forward in time, we can go back in time. So month, day is finite. It's got 365 possible values, right? So what I'm going to do here is we're going to have different rounds, and we're going to use a birthday attack. And the prediction is usually right around 23. entries, when we get to the 23rd entry, we'll have a 50% chance of trying to get a collision between something that you put in and something that somebody else put in here, just because of this probability theory that we test hashes for collisions using brute force and the birthday attack. So check it out. If I put in my birthday here, 115, and I'm just going to look at what you guys gave me. Alicia gave me 427. Amos gave me 718. Brandon is 25. Doug is 1231. Jennifer is, oh, Jennifer, what is that day? That's your birthday? Hot damn! Well, that's pretty awesome. So you and I, we have the same birthday. That's pretty cool. That's pretty cool. Because we have other things in common as well. We have other things in common as well. So there we go, Astro Twins. How about that? So if we just look at this here, the probability would be, the probability theory would be 23. So we got 1, 2, 3, 4, 5, 6, 7. So 21, 22, 23. We should have had a collision here before we got to the 4th round. It would have been a 50% chance that we have a collision before we got to Alicia's 4th entry here. But because Jennifer is super cool, she and I both had the one of the best birthdays around, Martin Luther King Jr.'s birthday. Now we are able to force a collision. Now, what does that mean? What does that mean? That means that if we're testing out a hash, right, a hashing algorithm, and we are able to plug in all these different text or files that are completely different, right? Each one of these is completely different. That if this algorithm is not good enough, if it has a finite key space, which some of them do, right? If it has a finite key space, then a collision will happen with a 50% chance or greater within 23 rounds of permutation. And so, in this case, we feed hello, and boom, that comes down here. In this case, we feed cyber, and that comes down here. Or, hey, we take 2 random people here that did not collude. We put in a random value here, right, into here, and boom, those 2 same people get the same output, which is kind of neat. I've been teaching for a long time, Jennifer. I've been teaching for a long time. And the only other time that has happened to me, where somebody else has had my same exact birthday, was when I was teaching over at Calhoun Community College about 10 years ago. So there we go. Let's keep on going here because this is kind of right up against lunch. I want to just kind of build out the rest of this real quick just to see if we have any other collisions here. Okay, so we have 1, 4. Up here we got 929. That's my wife, and then Alicia is 214. That's a good day. Amos is 630. Brandon is 511. Doug is 83. Jennifer is 1229. Ryan is, let's see, Ryan's 513. Ryan gave me pipes in between. I like that, man. 522 is my oldest daughter. Alicia is really close there. Capricorn, somebody. 117. Amos is 323. Let me know if you guys see a collision here, another collision. We might actually have another one. Doug is 8-4. That's pretty close, 8-3 and 8-4. You guys have a pretty good August there, it looks like. Jennifer is 7-5. That's a pretty good summer right there. Bunch of partying going on around in July. And then Ryan is 8-11. Okay, so after the third round of permutations, there's been one collision. And then Ben here, I'm going to do 319. And then Alicia, 317. Amos here. Amos put in 117. Boom, there we go. Look at that. Another one, another collision right there. So with each subsequent entry now, the probability goes even higher. So after 23, it goes to 50.2% or something like that. And then 24 is 51.9%. And then 25, it's 52.1. And then so it keeps going. The probability keeps going up with each subsequent entry that we put in here. And so it's over 50. It's pretty much a coin flip, kind of like a bingo game, if you will. There's what, 75 possible values. So, after 23, now after 23 times that it's red, now it becomes pretty straightforward that somebody's going to win very, very soon. Doug is 6-2. I'm just going to fill out the rest of this just for giggles and grins here. 9-23, and then Ryan is 11-10. So in this example here of the birthday attack, that's a test of a collision of brute force in a finite key space. This key space is 365, and you can see here within 24 rounds or 24 entries here in this finite key space, we've actually had 2 collisions. And so, from a deduction purpose here, if we were testing out an algorithm and we were able to put in random values here, these 2 collisions would immediately, we would lose trust, and we would tell that mathematician, probably, you suck, because that's the way people are, right? They want to be able to disprove anything that you're trying to do that's good. And that's the birthday attack right there. Any questions? All right. We're going to take a commercial break here for lunch. Today I want to do a little bit different, though. We're going to do a 45-minute break for lunch today instead of an hour. So come on back at 12:30 today, and we'll keep the dream alive. Okay, 12:30, and we'll keep the dream alive today. All right, we'll see you at 12:30. All right, welcome back. It's great to be back. Looks like it's another beautiful day for baseball. All right, before we get going, is there any questions up to this point? Okay, so that looks like a no. So what I'm going to do is go ahead and start this thing back up.